Hey everyone, welcome to your first flipped calculus video of the year. Today we're going to be focusing on a topic or concept called continuity. And so really we're going to be taking this idea of limits that we've been working with and extend it to this idea of continuity. Okay, so intuitively a function is said to be continuous if it has no holes or jumps. Okay. So for example, this would be an example of a continuous function. And really what we say is we know it's continuous if we can trace the graph without lifting our pencil. So I'm going to make a note here. It's continuous if you can trace the graph without lifting your pencil. Okay. Now, obviously, not every function is continuous. So if a function has a place where it is not continuous, we say that it has a discontinuity at that point. So if I were to look at this function over here, I can see there's clearly a jump here at x sub 0. So I would say that the function, I'm going to call it f of x, has a discontinuity at x sub 0. Okay. So now when we're talking about continuity on an interval, a function is said to be continuous on an interval if and only if it is continuous at each point of the interval. Okay, so again, going back to our example here, we know that f of x has a discontinuity at x sub 0. We could also say that f of x is discontinuous at x sub 0. And then we could also say on the converse where it is continuous. So we know that f of x, it's discontinuous only at x sub 0, so it's continuous everywhere else. Assuming, of course, let's say that these had arrows here. So we would say f of x then is continuous on the interval from negative infinity to x sub 0. Again, that's open because I'm not continuous at that point. And we're also continuous then on x sub 0. Again, I'm excluding that point from x sub 0 to infinity. So we can talk about where a function is continuous and where it is not continuous. And that's really our goals for today if we're looking at a graph to be able to define if it's continuous or not. If not, where are the points of discontinuity? And then what are the intervals where it is continuous? So let's go ahead and look at some graphs in the notes here. All right, I'm going to move this down a bit. Okay, so for number 1, let me focus this. So it says to find the points at which the following function is continuous and the points at which the function is discontinuous. So I'm going to just go from left to right here. So first I'm going to identify my points of discontinuity. Okay, and so if I move along from left to right, so far I'm doing well, but I notice when I get to negative 1, I have this jump here. So that's my first point of discontinuity. Okay, next, along this piece from negative 1, it looks like there's an asymptote here at x equals 0. So that's another point where I'm discontinuous. And now as I move along here, I can see I have a hole at x equals 1, so I'm discontinuous there as well. So I know where I'm discontinuous, so now I can define my intervals of continuity. And sorry about this, I'm going to try to focus this a little better. Okay, so now I can define where I'm continuous. And I'm on the intervals from, it's like negative infinity to -1. Now you'll notice I'm using a closed bracket here because since that point is defined, I am continuous there. So that's my first interval. My second interval is going to be from -1 to 0. And again, both at -1 and 0, I'm not defined, so I'm leaving those brackets open. Then I'm going to be defined between 0 and 1, both open. And then the last interval is going to be from 1 to infinity. Okay. So that's the first idea, is just looking at a graph, can you pick out where you're discontinuous and then correctly define those intervals where you are continuous? So we'll skip number 2 for now, and we'll come to that in class just to make sure we're all straight on this concept so far. Okay, so now let's go ahead and link this to our limits that we've been working with. So here we're going to talk about continuity in terms of limits. Now, we can talk about a function being continuous on the interior points, and we can talk about continuity at endpoints of a function. So the first thing we're going to do is talk about interior points. And what we say is we know a function is continuous if, and I'm going to say continuous, let's see, at a point C. So I'm just picking some arbitrary point C. So a function is continuous if the limit as x approaches c of f of x equals f of c. So in other words, if the limit as I approach that value is actually equal to the function value. Because you remember when we talked about limits, for this limit to exist, this value does not have to be defined or equal to the limit. But now when we're talking about continuity, that value of the function has to be the same as the value of the limit. And really what this means is it gives us 3 conditions for continuity at an interior point. For this limit to exist, I know that the limit as x approaches c from the left of f of x has to be equal to the limit as x approaches c from the right of f of x, and that has to be equal to f of c. So there is our definition, our criteria for a function to be continuous. Okay, so if I look at my example here, and I can just pick some arbitrary point C in this interval, since that value is defined, right, I can consider this point f of c. I can see both the left and right limits are tending to that value f of c. F of c is also defined, so I'm going to be continuous at that point C. Now, when we talk about continuity at endpoints, we say a function is continuous at the left endpoint of its domain or the right endpoint of its domain if, let's talk about the left first. If the limit as x approaches a from the right of f of x equals f of a. So in this case, if this were assuming this point was defined, in this case, we would say we're continuous at a. Similarly, we could talk about the right endpoint and say the limit as x approaches b from the left of f of x equals f of b. And again, if we know that value is defined, we would say this is continuous at both endpoints. Now, really quick, I just want to draw a distinction here. So I'm going to draw kind of similar to this graph up here. Let's say I had a very similar looking graph. I'm going to call this A and this B. But let's say my graph looked like this. Now, if I think about the left endpoint, I can talk about that limit as I approach from the right, but f of a is not defined. So I would not be continuous at the left endpoint. However, I would be continuous at the right endpoint. So So I'm going to make a note here that we're continuous at right endpoint. Let me make sure you can actually see this. Continuous at right endpoint, but not the left. Okay. So now that we know about discontinuities, we're going to learn 4 basic types of discontinuities. And each one is going to have a name, and we'll learn the characteristics of those discontinuities. So the first one we call a jump, which is pretty self-explanatory. And so the problem that we have here, if we think back kind of to our limit definition of continuity, we can see right away in this picture that the limit as I approach C from the left is obviously not the same as the limit as x approaches C from the right. So that's kind of the condition that fails here. The limit as x approaches C from the left of f of x is not equal to the limit as x approaches C from the right. And so we might see this with piecewise functions. The next one is what we call our infinite discontinuities. Obviously, we have a vertical asymptote here, which is forcing these portions of the graph to head up to infinity. So even though we could say the limit, I'm going to call this C, as x approaches C of f of x, well, both from the right and the left, I can see that's infinity. But that's not equal to the function value at C. Because of that asymptote, that is undefined. So I'm going to make a note. This infinite discontinuity is going to occur when we have a vertical asymptote. The next one is a removable discontinuity. And here's why it's called that. So we can again look at our conditions. It looks like the limit as x approaches C from the left and the limit as x approaches C from the right are the same value. So we do have a two-sided limit there at C. But clearly our function value is not the same as the value of that limit. And again, this is going to occur where we have a hole. Now, the reason it's called removable is because if I could just fill in that hole or redefine that one value, I could essentially remove that discontinuity. If we look at a jump discontinuity, we can't remove that simply by filling in one of those values. Okay, and the last one, I think we've talked about this a little bit earlier with limits. This is what we call an oscillating discontinuity because that limit as x approaches C of f of x does not exist. Because it's oscillating back and forth, it's not tending to a specific value. And we'll see this with some trig functions as we go through the unit. All right, so on the next page, we're going to go through one example, and then again, I'll save the second one. So hang with me for one more example here. So the only thing we're adding here, we're still using the graph to locate the discontinuities. Now we're going to actually go ahead and classify or name the discontinuity. We're going to use that limit definition to explain why it's discontinuous. And then we're going to identify where it is actually continuous. So let's go one by one, and we'll start with locating those discontinuities. So if I start from the left, the first point I notice where I'm going to have a problem is x equals -3. So that's my discontinuity. That one, since the limit from the left and the right agree, that's going to be our removable discontinuity. That's where I have my hole. Now, when it says to use the limit definition to explain why it's discontinuous, we would say that's just because the limit as x approaches -3 from the left, or excuse me, as it approaches -3, let's talk about that two-sided limit, is not equal to f of -3. So the two-sided limit exists, but it's not equal to the function value. All right, so my next one that I encounter is at x equals -1. Clearly here is where we have a jump. So that's our jump discontinuity. Now, my problem here is that the limit as x approaches -1 from the left of f of x, that is not equal to the limit as x approaches -1 from the right of f of x. All right, so now if I look from -1, my next one occurs at x equals 1. I'm going to jump up here. This one is also a jump discontinuity. Again, I'm going to use my limit definition. I know that the limit as x approaches 1 from the left is not equal to the limit as x approaches 1 from the right. Okay, now I'm going to keep going. So it looks like the only thing I have left is at this endpoint. And what I notice here is I am not continuous at this endpoint, x equals 4. Okay, now this one, if I could fill in this point, I could make it continuous. So that's going to be a removable discontinuity. And my problem again here is that the limit as x approaches 4 from the left of f of x is not equal to f of 4. Okay, so far we've identified all our discontinuities, we've classified them or named them, and we've used the limit definition to say why it is not continuous at that point. So the last thing we're going to do is identify our intervals of continuity. So let's go ahead and do that. Okay, so now I am closed here. So I'm going to say from -4. The first problem I have is at -3. I'm going to be open on that end. Now my next interval is going to be from -3 to -1. Again, since I'm open here, I'm not defined. That's an open bracket. My next interval I am defined on this piece at -1, so that'll be closed. And that takes me over to 1. Then my last interval here is going to go from 1, open, all the way to my endpoint at 4, which is also going to be open. So from today, our targets or goals were to be able to identify where a function is discontinuous, to be able to classify those discontinuities, use that limit definition to explain why a function is discontinuous, and then identify where it is continuous. So today we've been working largely with graphs. As we go on, we'll start to look at the functions. That's it for today.